Good morrow, fair traveller. I bid thee welcome on this finest of days to our third class of Unit 2. Now, as we've been warming up to inequalities over the past couple days, the ones we've worked with have kind of by design been pretty simple. But as nice as that simplicity is, especially if the problem solving we did in Unit 1 is any kind of indication, we should know that we'll probably be way more likely to find inequalities with a couple more moving parts. For instance, take this friend. The sum of a number and 7 is no more than 9. So 2 tasks for you. First of all, practice your skill of algebraic representation. Let's write this using some inequality symbols. And then, if I were to ask you to solve the inequality that you write, what do you think I'm probably asking you to do with it? Take 10 seconds, play around. Write this as an inequality, and then if I were to ask you to solve it, what am I probably asking you to do? Go ahead, play around, and then we'll chat. And stop. Well, first off, let's do my translation. Sum, the sum of, well, that of course gives me the operation addizione. I've got a number. I don't know what that number is. Let's call it n. The thing being summed with that number is 7. Is no more than here is going to be my inequality symbol. Well, if I'm no more than, hopefully we feel good about this translation by now, I cannot be more than, so I could be less than or equal to. And then on the other side of my inequality symbol, there's my 9. So n plus 7 is less than or equal to 9. Next, I've asked you to think about solving this inequality. And my hint to you, well, if it ain't broke, don't fix it. When we were working with equations, what was the goal of solving? What were we trying to do with our equation? What did we want to make it look like? 5, 4, 3, 2, 1. Well, when I was solving equations, I knew I wanted to make it true. The way that I made it true was by isolating the variable. So, chances are that I probably want to isolate this variable n. Again, our guiding principle in math is if it ain't broke, don't fix it. It ain't broke yet, so we're not gonna fix it. N plus 7 is less than or equal to 9. Look at this. What choice do you think that I might make here to get this n by itself? Go. Five, 4, 3, 2, 1, and stop. Well, n plus 7 is less than or equal to 9. I want to get n by itself. The thing connected to the n is the plus 7. How is it connected? By addition. Let's undo it using subtraction. Again, if it ain't broke, why are we bothering trying to fix it? To get n by itself, I'll subtract 7 from both sides. Here we'll see n should be less than or equal to, well, 9 minus 7 is 2. Does this make sense? Well, let's check. If I wanted to see if n less than or equal to 2 is actually my solution, well, I can always check my work by plugging it in. I've got 2 options here. Well, if I plug in that 2, because I could be less than or equal to, well, then this would become 2 plus 7. Is 2 plus 7 less than or equal to 9? 9 is equal to 9. So yeah, that one works. If I take something that's less than 2, maybe I'll try 1. If I replace this n with a 1, 1 plus 7 is 8. Is 8 less than or equal to 9? Well, yeah. So by checking our work here in both cases, we can see that this does in fact give us a true statement. Okay, that's great. But why does this work? Well, to visualize what's happening here, let's say that I take these 2 inequalities just with numbers. You tell me, why do you think I can, in this case, add or subtract some number from both sides of the inequality and still get something that when I check will turn out to be a true statement? Go ahead, play around. Are you done playing? Do you want more time to play? If you want more time to play, pause the video, play more. If you don't, if you feel like you're done playing, if you've lost your sense of childish joy and whimsy, then come back. Okay, let's say that I take -3 is less than 2. I don't know, I can take something random here. Maybe I'll add something to both sides. Let's make it really simple. Let's add 1. If I add 1 to both sides of this inequality, I'm trying to test and see whether I can still do the same thing to both sides. So -3 plus 1, well, if I add 1 to the left side, I get -2. If I add 1 to the right side, 2 plus 1 is 3. Is negative 2 still less than 3? Well, yeah, negative 2 is to the left of 3 on the number line, so this is still a true statement. I can try it with subtraction too. Maybe here I'll subtract, I don't know, let's do 10. If I minus 10 from both sides, I don't know, it could be anything. Negative 4 minus 10, well, negative 4 minus 10 is negative 14. In this case, is it greater than or equal to negative 7 minus 10 is negative 17? Well, yeah, on the number line, negative 14 is to the right of negative 17. So this is still a true statement, as were both of the statements that we begun with. So in this example, we can see that adding and subtracting the same thing from both sides still works. If it helps you to have a visual, right? Maybe I say take a number line. Let's say maybe I'm comparing two things, A and B. Well, say that I take A and then I add maybe 2. So I'll give myself some tick marks. We'll assume here that these are whole numbers. Well, if I add 2 to A, then I'd move 2 to the right. So I jump to here. Here's my new A plus 2. If I added 2 to B, bum, bum, I moved 2 over. Is A plus 2 still smaller than B plus 2? Well, yeah. And I could do the same thing working in reverse with subtraction. I'm just jumping the same number of ticks, in this case, over to either the left or the right. My inequality, or my imbalance in this case, is going to be the same. So the reason why this works is because this idea still maintains the original imbalance that was present in my inequality. So the way that we'll word that here, in this case, adding or subtracting the same thing from both sides of an inequality keeps them imbalanced in the same way that they were originally. From this statement, hopefully you agree with me, we can generalize the addition and subtraction properties, not of equality as we defined in Unit 0, but of inequality. So, in symbols here, let's say that I have something A and something B. And this can work for any symbol here. Maybe it's greater than, maybe it's less than, maybe it's greater than or equal to, maybe it's less than or equal to. It doesn't really matter here. But if A compares to B in some way, then we can establish, as we've seen above, that if I take A and I add some third thing C to it, and take B and add some third thing C to it, then once again the inequality still holds. Nothing about my inequality changes. The imbalance is as it was. And I've written this with all 4 symbols because it works for any inequality symbol. Given the way that we've written the addition property, see if you can write the subtraction property really quickly. Go ahead, take 10 seconds. Use some symbols. How might you express the subtraction property of inequality? And stop. Well, same idea as before. My original statement, I'm comparing two things, A or B, or A and B. Maybe they're greater, maybe they're less than, maybe one's greater than or equal to, maybe one's less than or equal to. It doesn't really matter. But again, the idea here is that if I subtract the same thing, we'll call it C, from both sides, then the original balance of my inequality is retained. Fantastic. So we know how this works for addition and subtraction. Knowing that they work exactly the same way as we'd expect based on what we know about equations, we should hopefully be left with a pretty unsurprising follow-up question. Well, if that's what happens for adding and subtracting, what happens if I try to multiply or divide? So take these two inequalities here. Knowing that the guiding principle, if it ain't broke, don't fix it, has not led us astray before, see if you could make a choice here to solve each of these inequalities for the indicated variable. Go ahead, take a minute. Talk to your partner, talk to the wall, talk to yourself. Who cares? Play around. Go, go, go. And stop. So let's say that I want to solve for C in this inequality. Well, that means I want to get C by itself. What's connected to the C? Well, it's being divided by 2. Hopefully we feel okay about multiplying both sides of our inequality by 2 to make this, in this case, get C by itself. 2 and 2 on the left side undo each other. I'm left with C is greater than or equal to 5 times 2 is 10. Well, let's quickly check this. If c is equal to 10, then I just need to check, well, is 10 divided by 2 greater than or equal to 5? That's 5 is greater than or equal to 5. 5 is equal to 5. So that works. Let's try something else. So in this case, when we were equal to, it worked. Maybe I'll take something bigger. So let's say something nice that's divisible by 2. Maybe I'll take 12, not too far from 10. 12 is bigger than 10, so it's part of my solution set that I've identified. 12 divided by 2 is 6. Is 6 greater than or equal to 5? Heck yeah, we're good. Now for our next one. Negative 3x is less than 6. Well, the thing connected to the x is the negative 3. It's connected by multiplication. To undo it, let's use division. So I'll divide both sides by negative 3. On the left side, negative 3 and negative 3 undo each other. I'm left with x is less than 6 divided by negative 3, which is negative 2. Let's check. So here, I'm going to take a number less than negative 2. Maybe I'll do negative 3. Negative 3 is less than negative 2. To plug in, I'll do negative 3 times negative 3. I want to check, is this less than 6? Well, negative 3 times negative 3 is 9, and 9 is... What? Wait, 9 isn't... 9 is not less than 6. What's up here? What's going on? This is weird, this is wonky, this is funky. I solved it exactly the same way that I would any equation, so why is it giving me something that in this case does not work? I didn't correctly identify my solution set. That's weird. So it turns out there's a bit of a catch when we're working with particular types of numbers doing multiplication and division. Addition and subtraction seemed fine, but to make sense of this, negative numbers are actually going to be the issue, right? I started by multiplying both sides by 2 with this guy up here on the left, but for the right, I divided by negative 3. Let's see why that gives us a problem. So let's take negative 2 less than 4. I've given you 4 different options here. Multiply, divide by either positive 2 or negative 2. Give yourself a minute, pause the video, perform each of these operations on both sides of the inequality. See what happens here. Just like before we looked at this in the case where we didn't have variables, can we make sense of what's happening if we think about a numerical case like this one? Take a minute, pause the video, play around, throw something at the wall, see what sticks. Go ahead. And stop. Did you get something that stuck? Well, let's find out. Negative 2 is less than 4 is my original inequality. So let's say that I take negative 2 is less than 4. I want to multiply both sides by 2. So I'm going to multiply on both the left and the right by 2 in example A. Well, negative 2 times 2 is negative 4. 4 times 2 is 8. Is negative 4 less than 8? Sure is. If we divide by 2, well, let's see. Negative 2 divided by 4. In this, or not divided by 4, negative 2 is less than 4. Let's divide both of these by 2. Negative 2 divided by 2, well, that's negative 1. 4 divided by 2 is 2. Is negative 1 less than 2? Sure thing. Now let's see what happens when we multiply or divide by negative 2. Well, times negative 2, this would become, well, negative 2 less than 4. If I multiply both sides by negative 2, maybe I'll write my multiplication like this time, who cares? Well, negative 2 times negative 2, this is positive 4. On the left side, 4 times negative 2 is negative 8. Is 4 less than negative 8? No. So in this case, multiplying by negative 2 actually causes us to flip our inequality symbol. Weird. So let's try it again with negative 2. In this case, I have negative 2 less than 4. If I divide negative 2 by negative 2, then that gives me 1. And if I divide 4 by negative 2, that gives me negative 2. 1 is not less than negative 2. It is, in fact, greater than negative 2. So the thing that we'll notice here that I hope you'll observe, what happens when I multiply or divide by a positive that's different from when I multiply or divide by a negative? 5 seconds, go, tell me. 5, 4, 3, 2, 1. Well, if I multiply or divide by a positive number, we'll start with the positives, we'll notice here that the inequality symbol that I use is the same. Nothing about the inequality fundamentally changes. It's still a true statement. But multiplying or dividing both sides by a negative number flips the inequality. So it changes, in this case, what side of the number line I'm working with. Weird. So like, to visualize here, if a visual helps you, say that I take my number line. Maybe, like, I'll just to work with some things here, A and B. Well, maybe here I'm comparing A and B. Notice here that A is to the left of 0, so originally it's negative. B is to the left of, or to the right of 0, so in this case it's positive. If I multiply both of these by a negative number, then that means I'm going to turn B into negative B and A into negative A. It doesn't necessarily matter where they live, on the number line specifically, but B is going to go over to the opposite side. A is going to go over to the opposite side. Notice here that I've flipped their positions on the number line. So if I'm doing a comparison where originally B was to the right of A, now the thing with the A is to the right of the thing with the B. So I need to change my inequality symbol to match how I've changed the positions on the number line. Great. So from this idea, hopefully you can see what's happening here. I can generalize this as I did above into the multiplication and division properties of inequality. I'll leave this up here for a little bit. So again, I might be interested in writing this in symbols. I think it's actually more effective if we write it in words. So notice, if I multiply or divide both sides of an inequality by either a positive number or a negative number, how does that impact the inequality symbol that I'm working with? Take 15 seconds, look back at your notes. How does this change the inequality when I use either a positive or a negative number with multiplication or division? Go! And stop. Well, hopefully you've noticed here, if I multiply or divide both sides of my inequality by a positive number, in this case, the inequality symbol that I work with does not change. So the inequality symbol will stay the same. Nothing about it needs to change as long as I'm working with a positive number. However, whenever I multiply or divide both sides of my inequality by a negative number, hopefully you saw from the examples we did above, instead of keeping our symbol the same, the inequality symbol that we're working with flips. If it's less than, it needs to become greater than. If it's greater than or equal to, it needs to become less than or equal to, and so on and so forth. Fantastic. With these ideas in mind, we should now have all of the tools that we need to solve any inequality that we can encounter. Let's start real simple, and then we'll get more complicated. Because of course we will. Math is about pain and suffering, and your pain and suffering brings me joy. Let's take this guy. 5/6 is less than p plus 1/6. I want to solve it, graph it, and write it in set builder / interval notation. So give me both of your notations here. Give me your graph, label your graph. Let's find our solution set. Go, go, go. And stop. Maybe you paused and played around with it. Maybe once again you didn't and you just sat here for 5 seconds in silence. Either way, it is of no consequence to me. I can't control what you do. I'm not your dad. So 5/6 is less than p plus 1/6. Let's get this p by itself. Well, the thing connected to the p is the 1/6. I want to undo it using a negative 1/6. On the right side, they undo each other. And on the left side, 5/6 minus 1/6 is 4/6. So I've got 4/6 is less than p. 4/6 is, of course, more simply stated as 2/3. 2/3 is less than p is my inequality. Let's graph it. So I'll give myself a number line. I'll label it with my variable p. I'll give myself a couple tick marks. In this case, doesn't matter where the 2/3 go. Maybe I'll put it kind of towards the middle. I'll give myself 1 or 2 things on either side to indicate some scale. Well, 1/3 up from 2/3 is 3/3, or 1. 1/3 down from 2/3 is 1/3, and I could keep going. In this case, 2/3, again, remember when I'm graphing, what's the question I need to ask myself? You tell me. 5, 4, 3, 2, 1. Very good. Well, I need to ask, is it in or out of the solution set? 2/3 is not equal to or less than. It's strictly less than, so in this case, the 2/3 is not included. Now here, P is on the bigger than side of the equal sign. The mouth, right, is opening up towards it, so P needs to be bigger than 2/3. On that number line, then, I need to be to the right of my open circle. Fantastic. So there's my graph. And then the last thing I need are my notations. Well, for my set builder notation, hopefully you remember, it starts with my little squiggly bracket. Really a brace, but squiggly bracket is more fun. Squiggly bracket here, I'm interested in all values of P such that, in this case, the only criteria is that 2/3 needs to be less than P. You could also write P is greater than 2/3. So there's my set builder notation. And for my interval notation, well, once again, I'm interested in the part of the number line that starts at 2/3 and goes off. In this case, it doesn't stop. It goes off towards infinity. Infinity, of course, is never included in the solution set. When things are not included, they get parentheses. 2/3 we've established is not included in the solution set. It gets parentheses as well. Fantastic. So let me give you 2 more to ponder. If you would like, you may opt out of writing these into your notes. But if you don't do them now, well, that's not my problem. Take these 2. Let's solve them, graph them, and express them in set builder and interval notation. Again, if you've decided that you're done, you don't want to write any more down, you're done with the video for today, that's great. And if you want to get a little bit more practice, well, here you go. Here's some extra practice. Let's take these 2 inequalities. We'll solve, graph, and write our 2 notations using our properties of inequality. Go ahead, play around. All by myself, don't wanna be all by myself anymore. I can sing better than that, I promise. Imagine if I get copyright striked for singing Celine Dion. Okay. Negative n over 4 is less than negative 1. I want to get n by itself. So here, I am going to undo my division by negative 4 with multiplication by negative 4. So I'm going to multiply both sides by this negative 4, and alarm bells should be going off for you because what choice did I just make? What did I just do? What number am I multiplying by? It's negative 4 because I'm working with a negative multiply or divide. What do I need to do to my inequality? I need to flip it. So I'm going to take this inequality, put it down, flip it, and reverse it. So in this case, my less than symbol is going to need to become a greater than symbol because I just multiplied or divided by a negative number. Well, on the left side, negative 4 and this negative 4, they cancel out. I'm just left with my n. And on the right side, I've got negative 1 times negative 4. This is positive 4. Magnificent. So n is greater than 4 is the inequality I need to graph. Let's take my number line. I'll label it with my n. I'll give myself a couple tick marks. Maybe I'll slot the 4 towards the middle. I'll say 5 and 3 off to either side. Give myself some ellipsis to indicate that I keep going. N is greater than 4, strictly greater than, so is 4 in or out of the solution set? Very good, invisible person. It is not included in my solution set, so it gets an open circle. N needs to be greater than 4, so once again, like above, I'm going off to the right. My 2 notations, my set builder notation, well, I'm interested in all values of n such that n is strictly greater than 4. And then for my interval notation, I want the part of my number line that starts at 4, ends at infinity, right? It keeps going. Again, neither infinity nor 4 are included in this solution set, so we get parentheses. And finally, 5f plus 1 is less than or equal to negative 14. Well, here I've got two things connected to that f, I need to figure out what choice am I going to make. In this case, like, what's the easiest thing to get rid of first? Well, just like solving equations, reverse PEMDAS is going to be the name of our game here. So I should probably try to undo any addition or subtraction that I see before I do the multiplication. So let's get rid of this 1. I'll get rid of positive 1 with negative 1. In this case, they cancel out, even though I'm using a negative 1. Remember, the operation that I'm using is subtraction. So I'm fine with the inequality. I don't need to flip my symbol here, even though the number that I'm operating with is negative. So I see 5f less than or equal to negative 14 minus 1 is negative 15. Now I've got to divide both sides by 5. Again, whenever I multiply or divide, I've got to make sure that I'm asking, do I need to flip my sign? In this case, is this a flip my sign symbol? Or is this a flip my sign case? Well, no. It only happens when I'm working with negatives. So dividing by positive 5 is totally fair game. Nothing about my inequality is going to change. In this case, f will be less than or equal to negative 3. So there is my solved inequality. Let's graph it on our number line. I'll label it with my variable f, give myself a couple tick marks. I'll put negative 3 in the middle. It doesn't need to be. It can be wherever it wants. We'll say negative 2 off to the right, negative 4 off to the left. In this case, is negative 3 in or out of the solution set? Well, it could be equal to negative 3, so negative 3 is in my solution set. My bubble gets shaded in. It's an answer on my test, and then I need to be less than negative 3, so I'm going off to the left. Finally, our home stretch, let's write our notations. I need my set builder and my interval. Well, for set builder notation, I am interested in the set of values of f such that, and again, my cheat code, I just slot my solved inequality into place. I need f to be less than or equal to negative 3. And then my interval here, well, f is less than or equal to negative 3. What part of the number line does that represent? Well, I'm going all the way off to the left, so I'm starting here at negative infinity. I'm getting really small, and I stop on the right at negative 3. Negative infinity, just like infinity, never included in my solution set, always gets a parentheses. Negative 3 is included in my solution set. The way that I indicate that in symbols is using my bracket. Fantastique! Congratulaciones! You did it. Have a lovely rest of your day, or night, or morning, or afternoon, or evening. I don't know. I don't care. Have a good one. I'll see you when I see you. Take care. Be well. Goodbye.